One thing that is differentiating from the type of test we do is that typically on classical testing, you have a machine which you call the universal test machine or a tensile test machine or rotating or bending, whatever. If it is tensile test, you have something, you have the shoulders on the specimen called the shoulders, and you have something that holds the specimen on this end, you have something else that holds on this end, like my hands. Now what you do is stretch and compress, and then you do this.
What's the degree to which you stretch, or does this vary depending on the test? I mean, how
depends
far?
on the material, depends on how ductile the material is.
Right, okay. So with a metal, I mean, obviously it's going to probably differ between the metal as well.
Yeah.
But are we saying like a millimeter? Are we saying a centimeter? What's the or even less than that?
On a coupon this size, less than that.
Even less than a millimeter.
Yeah. So my coupons, that's a good question. So how much are deformed? They are this size.
Okay.
The specimens.
Oh, because I suppose the actual size of the thing would vary.
Yeah. So the specimen is like this: a steel specimen, an aluminium specimen, titanium specimen is roughly this size.
Mm-hmm.
Okay. We're talking about 10 centimeters to 15 centimeters long.
Mm-hmm.
The diameter at the shoulders is 10 centimeters, and at the center is 3 millimeter. 1 centimeter, sorry, at the shoulders, and 3 millimeters at the center.
And it's this hourglass shape that you would describe.
So it's like pinky finger, the size of it. Yeah. So the amount that we vibrate it deforms is in micrometers. So you can't really see it. It's microns.
What's a micro? So I can visualize this. What is that as a fraction of a millimeter? Let's say.
It's 1,000 times smaller than a millimeter.
Right. Okay.
So thinner than a hair.
Mm-hmm.
So that's how much it deforms.
Wow.
And on the ultrasonic fatigue testing machine, you don't use two grips to deform it. Just fix on one, and then it relies on vibration. And that's why I brought this. One of the reasons is what we do is, let's say I have this ruler here.
Yeah.
And if I do this, it's vibrating at a natural frequency. So, which is low like this. If I increase the stiffness of the ruler, so this increase, it is quicker. So these specimens are designed, I play with the stiffness and the mass so that they work like tuning forks and they are vibrating like this at 20 kilohertz naturally. So if you would hit them with a hammer, they would vibrate like this at 20,000 cycles per second. That's the principle of operation. So they don't need anything holding them on the other end. They will just do it themselves. So the fun thing about this is trying to explain to people that's why I make the difference between load and stress. That's one of the differences. Typically on a tensile test machine, you actually load it, you apply a force to get the stress there. These machines, the load in theory tends to zero, but you still get the stress. That's the beauty of it.
That's the geniusness of it, is it?
Well,
so how?
It's based on modal analysis. I see. It's a different way of thinking. So when the funny thing is when you are thinking about engineering in terms of statics, like a static or quasi-static load that is being applied, or dynamic loads, so something that varies with time, it can change a lot the way you model the reality in the world if you are doing it in terms of dynamics or statics. That's just a curiosity.
I could talk about this stuff all day.
Yeah,
I'm probably still not fully understand it.
Well, it's like. So the thing is, like, if you are,
I'm gonna have to come and see this for real one day.
If you are pushing your kids on a swing, your daughter, who is now 6 or 7,
6 soon, in like next month.
If she's on a swing and she's not doing the work, you are pushing her, and you're pushing her as far as you can, until you reach a certain amplitude. Let's say it's a big amplitude. When you are keeping the motion, you are doing the force at the same frequency as the motion. You don't need to do a lot to keep that amplitude. But if you would grab and hold her statically, you would need to do a lot of force to keep her at that position. It makes sense?
Yeah.
But the motion is still there, or that angle is still achieved, if that makes sense. So because dynamic, you change the position, obviously. In statics, you keep it there. If you'd go now slowly in statics, you do it like this. This is quasi-static. You need a lot of force. Whereas if you are pushing slowly, as long as it is at the same frequency, of the motion, as long as it is tuned, the force is small. You don't need to do a lot of effort to get the motion. So those are the principles.
I can understand that.
Yeah, that's
That's a nice analogy I can get with.